Let's say you're eating a meal that has a whole lot of protein in it, but you're not in a space where you're trying to build muscle or build other proteins to do other things. Or what if you're using a whole lot of energy and all of the glucose that you had stored up has already been used? What happens to all the excess protein that you just ate? How do you make sure you're able to still use more energy? Your body is able to use ketone bodies, or where you have a carbon chain with a double bound oxygen somewhere in the middle of the carbon chain or not on the end, in order to make energy. Stay tuned. So to overview the major steps of how you make energy, you've got glycolysis, which converts glucose into pyruvate. That pyruvate can go a couple different directions. One thing that it can do is be converted into acetyl-CoA. The acetyl-CoA enters the citric acid cycle, and the citric acid cycle makes stuff that eventually goes onto the electron transport chain, and the electron transport chain makes a whole lot of ATP. Now, we mentioned that glucose isn't available, so we can't do that whole pyruvate to acetyl-CoA situation. We can't use glucose or glycolysis at all. So our focus is going to be on making things that can enter the citric acid cycle or things that can enter the electron transport chain. Both fatty acids and amino acids can make acetyl-CoA through a process called ketogenesis, but the way in which they make the acetyl-CoA is going to be a little bit different. In order to understand how ketogenesis works, it's first important to understand why you got to make ketones in the first place. The way acetyl-CoA is set up, it's not able to travel through the blood on its own. It has to be attached to a transporter. In order for something to be able to travel without the transporter, it's got to be hydrophilic or water soluble or able to do hydrogen bonding because the blood's mostly water. So ketones are able to do hydrogen bonding, but the bigger the ketone gets, the less likely it is to do hydrogen bonding. So you need to have really small ketones in order to be able to travel within the blood. The two major ketones that travel within the blood are acetoacetate and beta-hydroxybutyrate. Different molecules are going to make different things. Every fatty acid is not going to make beta-hydroxybutyrate. Every amino acid is not going to make acetoacetate. Depending on what you start with is going to determine what you end with. But in general, they're all going to have that 4 carbons with some things attached to those 4 carbons. Acetyl-CoA is 2 carbons with stuff attached to it. So to go from the 4 carbons to the 2 carbons, you got to split in half. But the main point of getting to acetoacetate and beta-hydroxybutyrate is to be able to convert them into acetyl-CoA once they enter the target cell. One example of this reaction is how leucine is converted into acetoacetate through a series of reactions. You can see an overview of these reactions here. But if you want a better understanding of how not only leucine creates acetoacetate, but every single molecule can get converted into some type of ketone, check out reactome.org, which is linked in the description below. Now, most of the time, creating these ketones, you heard me say 8 at the end of those words, which means they are COO minus and they have a negative sign in them. So there's a negative charge. If you have a whole lot of ketones, it's going to make the blood overall become more negatively charged. Other parts of your body are set up to be able to balance that anion by having something called a cation around to offset those charges. When the hydrogen concentration changes, that's what makes the pH of the blood change. So if you have these ketones that go on to be unregulated because of this balance of the negative and positive charges, you can end up having something called ketoacidosis, or when your blood gets too acidic because of the ketone bodies being present. To get a better understanding of ketoacidosis, check the video linked in the description.